Well, let's say here, in this simple example, what you should do is that instead of having a fixed v, depends only on the position and not on the time, if you have interaction, you should put something which depends on the time t and on the position at time t. Yes. So pause work. It's a force. If you want to go from the potential to the force, instead of having a force which is constant in time, it varies. Suppose that you have two planets and the interaction between the two planets. Of course, if you express things in a frame where the mass center is fixed, their attraction is constant. But if you want to the Earth and the Moon, of course, if your system is centered on the Earth, then you have constant force at a given place. But if you take into account the fact that the Earth is moving, and you take the Sun as a center of your frame, then of course the gravitational force varies in time, because it's a gravitation exerted on a given part of space in the solar system by the Earth which is moving. That's the idea.
But the formula suggests just u naught of t, v, u naught of t.
Yes.
It's just that v evolved into the free evolution, which is why it goes to zero rapidly with t.
So, okay. Now I will go to Feynman passing integral, and so this is, of course, it's what Dyson took out, and this is rigorous. This is rigorous. Of course, you have to work to make the necessary estimate for conversions and so on, but the method is rigorous. So what? Yes, another method which was used by Feynman in his thesis, and is the one that Cécile and Marcel do not want to use explicitly. So it's discretizing time. Discretizing time. So you want to see the evolution, so you have your curve, which has an evolution from initial times, let's say 0 and finite time t. So what you do, you replace this curve by a polygonal curve, which is a familiar procedure, polynomial curve. Polynomial curve by subdividing the time interval into small pieces. Now, what you imagine is that the intuitive idea is that in this small time interval, the system moves without the force. And the action of the force is to kick. Instead of having a continuous action of the force, depending on the potential, you imagine it's some kicks at fixed time. So here, the kick will produce a change in the velocity. Instead of having a continuous change of velocity, you imagine that you move at fixed velocity for a time, that means you don't take into account the potential. Then you are kicked, then you change the velocity, etc., etc. So instead of a continuous action of the force, you have various kicks. Of course, Newton believed that. When Newton derived his equation, he got this idea. Okay, so now the fact is that this is for classical mechanics. So you move at a constant speed, and there's a kick, you change the speed, etc., etc. In quantum mechanics, what you do, you let the Schrödinger equation work over this time interval without the v, without the potential. Then you make a you make a change. Okay. And you make a change which is obtained by, instead of having a kick, you put a factor which is ei v at vt over h. That means you take into account the part of the action which comes for the potential, and then you don't make use of it until you end up at the end of your small time interval. So you correct, instead of having the continuous relation. information you collected at the end. Okay, and that amounts to the following, that it amounts to replace the action, the action which is this one, by a discretization, which is as follows. So you have the intermediate time 0, t1, etc., tn, t. You have the corresponding position x1, xn, etc., x0, xt final. And then instead of having what you have, you replace this integral by a Riemann sum, which is the following. The Riemann sum is sum over I of what it is, n over 2, xi plus 1 minus xi squared, minus I squared, divided by ti plus 1 ti minus ci, which is a discrete form of integrating n over 2 x dot squared dt. X dot is dx over dt, well, that is dx squared over dt squared multiplied by dt, so it's dx squared divided by dt. The action can be written formally as integral m over 2 integral of dx squared over dt, etc. So we replace this by this, and then you have to add the corresponding term, which is let's say vxi multiplied by ti plus 1 minus t. So we suppose that the potential remains constant in this one parameter. So this is what formally what you get in the action. But when you solve the Schrödinger equation, instead, what you have, you solve the differential by this interaction method. You let the wave function act according only as a free particle for a short time. Then you put a factor, which is an exponential factor of Vx, etc. So the fact is that it's known, an explicit solution to the Schrödinger equation without potential is known, it's classical, and then you apply it and you do some calculation, and formally what you get is an integral of I exponential over h bar, and let's say s of some path gamma and d gamma. G gamma is obtained as follows. It's a limit which doesn't exist. If you replace if you split the time interval into n pieces, the function x of t is replaced by the set of value x1, xn. Then ds, you have dx1, dxn. And then you go to a limit by letting the time interval become smaller and smaller. Okay. Whoa.
So normally we stop at 1, but let's say we go to 1:20, but then we have to cut it off because we also have to go to lunch before the
Okay. Thank you. Okay. Well, I spent too much time for the preliminary. Now I have to come to what I did and what Cecile did, what we did together. So all this is known. All this is Now, what is our strategy? Our strategy is to use Fourier transform in infinite dimension. For the physicists, this is a use of sources and a Schwinger functional. So Schwinger dependent on sources. It's everyone knows it's a kind of Fourier transform. So it amounts to, if you have a field and a corresponding action, to add something which is linear, let's say J phi, something linear in phi, and then replacing the action by this one and looking at the way it varies in terms of J. And since you have some variation, you can do calculus of variation and apply the method of the principle of Schwinger to that. Okay, so that's motivation for physics. But now Fourier transform. Now I come to the mathematical development. So as I said, it's the same as Schwinger source. But the first point is Schwarz space S of R, Rn. Many Schwarz, this one is Laurent Schwarz. So, okay. And it's maybe it's better, it's best discovery. So you have in fact in n dimensions you have vector x with coordinate x1, xn, and the corresponding derivatives are called d1, dn, first order partial derivative. And you are interested in the space which of functions which are small enough at infinity so that the Fourier transform makes sense, and which are regular enough at infinity, regular enough, emitting enough derivative, so that the Fourier transform should be again small at infinity. Okay, you know that in Fourier transform, if you multiply by x, the Fourier transform is derivative. It's a derivative. So, okay. So we want to combine it. And this, what Schwarz did is the following. Well, I will show n x alpha for x1, alpha 1, xn alpha n, and g alpha for g1, alpha 1, dn alpha n, monomial in the coordinate of the derivative. And Schwarz's definition is that you look at the function phi of x such that if you multiply it, if you apply a derivation, higher order, and multiply by a monomial, this remains bounded over all space. A function such that it admits derivative of all order, and if you multiply any such derivative by a monomial, is bounded. So it's a definition. But the fact is that if you do the Fourier transform, well, the caveat, my Fourier transform is always normalized by phi of x e 2 pi I xy dx. This is phi at of y. Why is this 2 pi I? Because, well, I've done number theory, and the Poisson summation formula is expressed in a neater way if you do 2 pi I. But more important, we will have to go to infinite dimension. And I want formula in a space with a growing number of dimensions, but no constant will diverge. If you use various normalization of the Fourier transform, you may have a factor like pi to the n in n dimension, and they will explode when n goes to infinity. So this is the way to do. Okay, so we do with this Fourier transform, definition of the Fourier transform, and of course the 2 pi r makes that if you apply twice the Fourier transform, it's the original function. No constant, no more constant. And so, okay, now this is just a small thing. If you have, and you know that if you multiply a function by a coordinate x, the Fourier transform is derivative, you get the derivatives corresponding to Fourier transform y. And if you derivate multiplication. So it's obvious from this very easy property that the Fourier transform must map S of Rn into S of Rn. Well, I want to be a little more because I have to go to do things independent of coordinate. So I will choose E, which is an n-dimensional vector space, real vector space, and define S of E, which is easy to define. It's independent of the choice of coordinate. And the Fourier transform maps this into S of the dual space E prime. Or if you want to coordinate, you have a vector x with composite xi and a vector y as composite yy. Summation, right summation. So S of E and E prime. It's quite important. In finite dimension, you can always choose coordinate, but in infinitely many dimensions, not always possible. So you have a map from this to this, which is reversible. So you can, if E prime is a dual of E, then E is a dual of E prime. This is well known. So you have exchange Fourier transform. Now you would like to have a distribution. So first of all, this going to distribution. So S of E is naturally endowed with a certain system of norms, infinite system of norms, and so it makes sense to speak of the dual. Linear functional which are continuous with respect to a system of norms. Not one norm as in the one aspect, but a system of norms, which takes into account more and more derivative. Okay. But now it's very easy to show that once you have a space and so the idea is that S of E serves as test function, and that the distribution, an element, is a linear form on test function. Well, T of X makes no sense, but integral Tx phi of x dx, which phi is a test function, makes sense. And by the way, this is the definition given in the book of Dirac. Dirac has a comment of what he means by delta, and the comment is right. Except that he did not come to describe precisely what is a space of test function. But the idea that there are test functions, and that what you consider is not here at a given point x, but such an average, is explicitly in Dirac.
But he said, when I asked him about the Dirac delta functions, that he was an engineering student, and they always differentiated heavy side functions. That was Dirac's sense.
That's also possible. That's also possible. Okay.
So is this S prime, is this distributions or just temper distribution?
Temper distribution. No. There is a larger set. Well, the larger set which are distribution in general, which is larger, we take less from the quark. But this one is adapted to Fourier transform. If you take a general distribution, the Fourier transform is not defined. But for this, so S prime is a set of so-called temper distribution. But this is a little too general for our purpose, and we would like to have, at the cost of breaking the full symmetry between N and E prime, because S of E, S of E prime, and S prime are defined similar way for the space and the dual, I will break this symmetry and define the following. An integrable distribution is defined as follows. I take a distribution T in S prime, S of E prime, temper distribution. I define its Fourier transform T groove, which is a temper distribution on E prime. But it is known that distributions are generalized functions, which means that we know how to identify a function with a distribution. Of course, where was it? So if T is a function which is not too big, it doesn't go too fast at infinity, and if you multiply it by a test function, so that you can integrate, then any function T of x defines a functional on test functions and defines a distribution. So it makes sense to say that a distribution is a function. And now the definition is as follows: T integrable if and only if T proof is a continuous function. Well, it cannot be an arbitrary continuous function. It's a continuous function which is not too big at infinity. It doesn't grow up stronger than the power of the coordinate, another monomial. So it's bounded, the function is not bounded, but it's bounded by a suitable polynomial. So it's continuous function bounded by a polynomial. And each such function qualifies to define a distribution, temporal distribution. So if you take such a function which is bound and continuous and bounded by the you go backwards and you get a distribution. I call such a distribution integrated. Why? Well, what are the properties? What are the properties? First of all, if a function f is in L1 of E, integrable in the Lebesgue sense, I say it's an integrable distribution. Why? Because if f is an integrable function, f, the Fourier transform, is known to be continuous. That's Riemann-Lebesgue lemma, going to 0 at infinity. If you take an integrable function in the sense of Lebesgue, its Fourier transform is not only continuous, but goes to 0 at infinity. So, an integrable function satisfies this, and therefore it's integrable distribution. Second, if you derivate, if you t is integrable, and you apply a partial derivation of any order, it's again integrable, because it amounts to multiply t roof by a polynomial. And according to our property, it's clear that if t roof satisfies this property, you can multiply it by a polynomial, it's still satisfied. So you are allowed to have the freedom to multiply by a polynomial here, in the other one you have here. So what you have is that, let's say here, so you have integrable function, you have kind of derivative, as it was said, I mean, for Dirac, the purpose of generalized function was to the possibility of deriving any function. That's okay. And it's almost optimal, so, and taking finite sum, etc. So, okay. So it's really a description of this integrable distribution. But you see, there's a dissymmetry. It's integrable, they are continuous. So you cannot invert. But let's say, if your function, if your distribution is support, well, it's a so for instance delta, the Dirac delta Fourier transform is 1, so it qualifies. Delta, but the derivative of delta qualifies, and you may have, you can imagine combining these two properties, you get a lot of it. Okay, so that's But there is one more property which is crucial for our application. Suppose that you have E1 and E2, two vector spaces, and P, which is projection. That is, it's linear, and the image of E1 covers all of E2. Or if you want, you can select coordinate system, if you have more coordinates in E1 and you to go to E2, you omit certain coordinates. You forget certain coordinates, not what I call it the projection. Now, it's well known in probability that if you have a probability law U1, well, I did not say, but not only an integrable function, but also, according to Borgner theorem, a probability law, a measure, a bounded measure, qualifies as an integrable. And what we want is a generalization of probability. And so, if you have in probability, if you have a probability law U1, and so you have probability, that's a probability law of a random variable x, which is x1, which is takes value in 1. Then if you have mu2, and you define p of x1 is x2, so you apply the projection to the coordinate of your random variable, or random vector, sorry. You have a random vector, you apply the projection to the coordinate of random vector, you get another one. And the probability of mu2 of x2 is obtained by a certain procedure, analytic procedure. So, and the procedure is defined in such a way that integrating f2 over e2 with respect to mu2 is the same as integrating over e1 of f1 d mu1, but f1 is obtained as composed by composition. Yes, if you have f2 over real values and f1, that's the diagonal. f1 is obtained by composing f2 and p. So that's the definition of an image of a probability law. And we would like, because we want to generalize this. Well, you know, in probability you have Gaussian law x squared dx. But they correspond, they Gaussian law, they are well defined, positive, they define probability with a suitable constant. Here we are interested in something which is ix squared over 2. Because they are in the action, you have to put the square root of -1 divided by the constant, point constant. So you have, instead of this, you have to deal with this. Fortunately, so that's a very primitive case in one dimension of what we are looking for in infinite dimension. But we are fortunate enough that if you take this, of course, this is an oscillating function, which is everywhere about modulus 1. So the Fourier transform in the ordinary sense cannot exist. It's not integrable. It's not absolutely integrable, because the absolute value is 1. But if you take the Fourier transform in this sense of Schwarz, it exists. And miracle, in the same way as E minus x squared as Fourier transform E minus or rather 1. According to my convention, pi x squared as Fourier transform minus pi squared. That's one of the advantages of normalization. And it's similarly, pull pi x squared as for Fourier transform E minus I to change I to minus I pi squared. What is the advantage? If I replace a number x by a vector, x squared by the dot product of vector with itself, the formula is true independently of the number of dimensions in the same. That's the advantage. That's what we choose in normalization. Okay, so now we are